Ladies and gentlemen, peaceful revolutionaries, this is Sylvain Rochon, the peaceful revolutionary. I'm here coming at you from Ottawa, Canada. Still there. I may move around in the next few months, I don't know yet, but still through the internet, we're all connected. Anyway, this week what I wanted to do is I wanted to talk about some technological advancements. And I have a list of different links that I kind of gather, and they kind of stack up because I don't have time to do more than one video a week. But I try to take the juiciest and most interesting bits when I want to do a technology blog. Now, this is about organic computers. What's really cool is this. Research on organic computing has been going on for a number of years, primarily just trying to figure out components that would replace the mechanical computers that we have, silicon chips with the gold lines to transfer the electrons, the gates that makes the ones and zeros, so that the computer language, which is all ones and zeros, as you know, memory, things like that, but using organic molecules. Now, people usually get confused when we talk about organic computers. People think about a living creature of some sort that acts as like a computer, a little bit like a pet. That's not the case. I mean, it could be. Because we're biological computers, like our brain is a biological computer, and we have all sorts of biological components that do different things, that enact what the computer is thinking and what it's doing, that kind of deal. So yes, that's that is a possibility, and it is a type of organic computer like our brain. But we're talking about something way more familiar. We're talking about essentially replacing the components of your current computer with organic molecules. For example, there's been significant research about organic memory, and the most interesting successes I've seen so far is using DNA, which is in a way memory of our cells. So we're using the same enzymes as found in cells of the human body, and the properties of DNA to store information. And DNA has 4 base pairs: A, T, C, G, adenine, cytosine, guanine, and thymine, or thymine, I guess in English. So it's not binary. It's I guess it's 0, 1, 2, 3. Or if some research, what they do is they say, well, okay, A and T is 0, G and C is a 1, so it becomes binary. And what's really neat about DNA as a way to store memory is that you can have DNA molecules that are all crunched up together in a liquid form, because it's like viscous. It can be in solution, and all and we can use sequencing machines, which we've been using since 1999-ish, to sequence the human genome, for example, that kind of deal, to create new strands of DNA that essentially can be translated to ones and zeros, right? And there was a really cool article, and I put the link down below, that is fairly recent. Let me check the year here. This is 2012, so not that recent. But it's a research group out of Harvard. What they did is that they did exactly what I told you. They have like DNA strands, and they also encode with a certain amount of base pairs in the first part of each DNA strand, a bit of code that is certain length. I can't see. Anyway, it's a small bit of code that essentially acts like an index. Those of you who know programming if you want to find your data on your hard disk, you have to have some kind of index. You have to know where it is, and you have to have some kind of way for your hard drive to kind of find that part of information, extract it, and read it. So with DNA, what they did is that they have a special sequence that is a certain length, that is always the same length at the start of a strand of DNA. And so when you're looking for a certain piece of information, you look for that index. You latch on using molecules, enzymes. It's looking through a liquid, essentially a beaker, or a glass of water, with some water in it, and your molecule is swimming into that beaker, or that glass, that solution, and looking for that specific strand fairly quickly. Then when it finds it, then it latches on the enzymes that duplicate the DNA to get the information out. Now, one of the things that they discussed with the Harvard guys is that what's really amazing is that in a gram of DNA, they're able to get 700 terabytes. Terabytes of data. Essentially, it's 1 gram. So in a droplet of water, essentially, or the size of the tip of your pinky, you have as much information capacity as 14,050 gigabyte Blu-ray discs. That's huge, right? If you put that in a hard drive, in 3 terabyte hard drives, for example, the hard drives that would be needed to get that information, to store the information, would weigh 151 kilos. Now, this, using DNA, it's 1 gram, and it stores the same amount of information. Now, the downside of it is that traditional hard drives are way faster to store the information, get information out, than the DNA counterparts. But if you're looking at long-term storage of information, DNA is awesome, because it takes like a small amount of space, and you have like huge amounts of information, and it's super stable. Hard drives are less stable than DNA strands. DNA molecules. So you can come back to your solutions, I guess, of DNA 100 years from now. The information would still be there intact. That's how stable that is. So that's really cool. That's a component. That's the memory component. They're still working on it because it needs to be faster to be practical with computing itself. Now it could be used potentially right now as a storage device for long term, but we need fast, right? We need speed. Now, what's really cool with organic molecules and how they work with electrons is that you can go beyond the limitations of silicon and gold chips. Because one of the issues you see with chips, with microchips, is that there's just so many gold wires you can put into a silicon wafer at a certain length, distance to each other, before you get interference or you get short circuits and things like that. Because it's like 2 live copper wires, for example. If you put them right next to each other, eventually they're close enough that there's going to be sparks and arcs, and then the information gets screwed, and then you get short circuits and things like that. So that with the gold, is the same thing. It's like live wires that don't have any insulation around them, because you want to be as tight as possible. You want your microchips to be really, really small, right? There's some molecules, organic molecules. What they do is that instead of going through a metal to transfer electrons from point A to point B, because that's what you need to activate gates, like to say like 1 and 0s inside a computer chip. You have to send electrons. If there's an electron that goes by, that's a 1. If there's no electrons, it's a 0. That kind of deal. So you're not using gold wires or copper wires or anything like that. You're using molecules that are essentially within the molecule. These are kind of molecules. Is that you have like a chain of electrons that kind of piggyback each other, in literally like a chain. So if you put some pressure of a single electron at one end of a molecule, of one of these organic molecules, they kind of chain internally inside the molecule, like inside the atoms. And at the very end, there's going to be one electron that's going to be pushed out, essentially, to put pressure on the next molecule. So you can create wires that are one molecule wide, chain them, and then you have an organic wire that transfers one electron at a time from one length to the other. And then these organic wires, you can put them as close as you want together. And this is like 3 or 4 atoms wide. Very, very small organic wires. And you put them right next to each other, the electrons will never jump from one molecule to the other because that's the way they go, not sideways. Okay, so you can create these wires that are like super, super dense, super small, like very small, and I wouldn't be mentioning it, this concept unless we had a breakthrough. And it turns out that in Canada, this is University of McGill. They some researchers there. This is an article from this year. It's very recent. It's 2016 or end of 2015. Sorry, Professor Dan Nicolau of McGill University. They created the first prototype organic computer, which means it's fully functional. Because, like I said, we've been dabbling with components of organic computers for a long time. This is still a prototype. He says it's about the size of a small book. But it's designed in the same way as supercomputers of the traditional kind, and it works. So it's the size of a book, and very small, and it has huge computing potential. And they still have a lot of work to do, apparently, to make it happen. But it's great. And like some people have been asking me about organic computing. They say, well, since it's organic molecules, do you have to feed it? Like I said, this is not a pet. The molecules are organic, but just like water, the water molecule is an organic molecule. You don't feed water. Okay, it's when it becomes like cells and things like that, like the way we're built. That's when you need to feed it. But these computers, they need energy, just like any other computers, to kind of do what they need to do to transfer electrons through a chain, for example. Well, you need energy to do that, and that energy can be, the same energy as like your wall outlet as for traditional computers. There's a bunch of ideas of using adenosine triphosphate, for example, as an energy source. For organic computers, but you're going beyond the normal, so it becomes more complicated. The ideally is that you're just at this stage just replace the mechanical components with organic components, so that they have the stability, the miniaturization. You don't have the interference and short circuits, and these computers, including this one from McGill University, doesn't heat. Because electricity is not going through a wire that heats up. It goes through organic molecules. It doesn't heat. So there's no heat problem, and you don't need a heat sink and things like that, which is another limitation of traditional computers. These things heat up, and the more gold wires there are and more microchips there are in a small amount of space, the more heat, and then it can get too hot and all that stuff. So organic computing, very cool, very real this year. And there's going to be other groups that will advance on these computers, essentially replacing components with organic components. And we're going to see soon after, once we get a handle of that in 2, 3, 4 years, maybe, we're going to start seeing devices that are organic in nature, that are 1,000 times smaller than ever possible using traditional means, which means you can have nanorobots or transmitters or things like that will circulate in your bloodstream in tiny format to support healing, to help with your internet, whatever, or communicate with different parts of your body and the outside, like your smartphone, things like that. We're going to be able to see all sorts of really funky things going on in the next few years if this kind of continues. So stay up to date. I'm going to keep my eye on this stuff because this is really really awesome. I mean, one of the blogs I did maybe a year ago was about the singularity in 2029-ish, according to the futurists. I mean, organic computers could be a way to accelerate that, where you have computers that are just as fast. They can make just as many computations a second as a human brain, for example. That's the definition of the singularity, and being able to free ourselves from manual labor, from doing all sorts of stuff, by AI that is not cumbersome, not heavy, not that doesn't overheat, doesn't require huge amounts of electricity, but as just as smart as we are, or even smarter, using organic materials. So very nice, very cool. Stay up to date. I'll keep you up to date for sure. And anyway, that's going to be it for today. I think that's enough. Just a small note: I won't be making a video next week. So I'll be on vacation. But the week after that, for sure, I'll make another video on some topic of interest. All right. Stay frosty and keep the revolution going. Ciao for now.